Yes,
like this?
okay.
Okay, thanks. Yeah, so I would like to thank the organizers for being so brave and bring us back to real life. Yeah, so I will talk about work which is very different from what you heard previously. So after spending some years on the subject that Benjamin presented a few minutes ago, I decided to take some vacation from that subject and do something, go to Australia and work on the subject from my childhood, long-range integrable models with my PhD advisor, Vincent Pasquier, and with my colleague, Jules Lammers, who is very energetic and who pushed us to come back to this to some project, to some problem that was still open since the 90s. So it's about deformation of already a long-range, complicated model, which is a long-range model. So you heard many times here about long-range interacting models. They appear not only in ADS-CFT, but also in condensed matter theory, in random matrix theory. They appear in many instances, and very few cases are completely understood and treated as the nearest neighbor interacting models are treated in an algebraic framework. So one of the purposes of what we are trying to do is to get a unified framework for nearest neighbor interacting model and long-range interacting models. And well, there is a very tight, beautiful mathematical structure which helps us to do this thing. It's called the double affine Hecke algebra. So I will use this object in my talk, but somehow the fact that you have this very beautiful constrained object means that you are not free to look at other deformations. And another motivation to study this model is to understand the separation of variables for long-range interacting models. There was a lot of progress recently on the separation of variables, and the long-range models are still somehow out of the reach of this progress. So now here I will present a particular model, which is a kind of XXZ deformation of isotropic model that we have studied for some time. So before going to the q-deformation, I will try to explain you what is the Haldane-Shastry model, because I suppose that in this community it's not so well known, and it's not so well known in other communities as well. So we are talking about a model which is an interaction of spins, n spins on a circle with periodic boundary conditions. So the spins are located at the position of, at the roots of unity, if you want, on the circle, nth root of unity. And the interaction between the spins is given by the usual spin permutation, like in XXX model. The only difference with the Heisenberg model is that this potential here connects not only the nearest neighbors, but any two spins on the chain with this kind of potential, 1 over sine square. And this model has the property that it's, if you want the simplest model you can imagine with interacting spins, because the spectrum is very much like a free spectrum of free particles in the sense that already you have this additive expression for the energies. And then the individual energies are can be written in terms of integers. Mu m's are m integers, capital M integers, which are the in some sense the moment of the m magnons. So you can encode the spectrum of a particular state in this capital M numbers called, you can call them rapidities, like in XXX. So the different mu's are constrained by the fact that they are separated, but by at least one unit. So the most packed way you can choose them is to fill every other orbital in this capital n-1 set of allowed momenta or rapidities. So first remark is that there is no space for bound state left in this picture. The rapidities are all real, and the interaction is like only statistical repulsion between these different momenta. And this collection of integers which take value from 1 to capital N-1, they are called, so this collection is called a motif. And the motif can be also alternatively described in terms of a partition, lambda, with parts which are ordered, weakly ordered. So the different lambdas can be equal or different integers. So you see that in order to be able to, sorry, make room for all the states, you have to have a huge degeneracy, and this huge degeneracy is explained by the fact that the Hamiltonian, this Hamiltonian, does commute not only with the SUN generators, but with a much larger group, which is much larger set of generators, which are the generators of the Yangian. Yes.
So the mu there, I can think of that that you wrote at the bottom as a dispersion, and mu is from 0 to n or something like that.
Yeah.
Sorry.
Yes.
Okay.
Yeah. So this would be the vacuum, like the lowest excited state, kind of vacuum, and then you can just push your mu's at higher values. Yeah. Okay, so that's the model, and the Haldane-Shastry model, and it's not an isolated model, but it inhabits a whole family of long-range models, which bear the name of Inozemtsev. So what changes for the different models is that the value of this coupling between different spins, let's call it potential. So it's a one parameter family which interpolates between Heisenberg model and the Haldane-Shastry model. And there is a parameter which can be parameterized alternatively with this kappa or this omega. It depends on the use of the object you are looking at. So in the case, in the general case, this potential is elliptic. Is the Weierstrass elliptic functions with two periods. One is the length of the spin chain, And the other is this imaginary parameter here. Kappa is imaginary, kappa is real, omega is imaginary. So if you take different limits of this elliptic potential, you can go, so if kappa goes to infinity or omega goes to 0, you go to only the nearest neighbor interaction survives. If you send kappa to 0, you get this trigonometric or Haldane-Shastry model. If you send the length to infinity, then the potential becomes hyperbolic, and it's a little bit easier to study this model. This hyperbolic model is easier to study than the full elliptic model, because what we call the wrapping corrections are absent. Exponential correction in L are absent. And you also, you can take the two periods to infinity, and then you get the rational 1/z square potential. So all these models are related through periodization in different directions and different limits. So the nice thing is that the limits, these two limits, Heisenberg and Haldane-Shastry, have algebraic structure. There is a monodromy matrix. There is some algebraic Bethe-Ansatz structure that we can use to solve the model. This one is much more complicated in the sense that the algebraic structure is still missing. It's too complicated, but still this model is useful to interpolate between, to get information, to see how the structure of, oops, it froze, the red point froze, but I hope it will, okay. No, not on my screen, but on the, okay. We are catching up. Yeah, so this the study of this elliptic model can be used to interpolate between Heisenberg and Haldane-Shastry. There was a nice paper this year by Jules and Rob Klebers about so they reconsider the problem of two magnons for this complicated model, and they got a few interesting results that simplify the old results of Inozemtsev and his collaborators. So that's that was to situate a bit the object I'm talking about. So now, if you want to solve this model, you better go to some more general model where the position of the particles can change. So it's a dynamical model, and it's called the spin Calogero-Sutherland model. The solution of this model was obtained before I started my PhD, or the year when I started my PhD. And you see, this model has a parameter beta, and when beta is large, this potential is very strong, and will tend to fix the particles at the equilibrium position, which is exactly this freezing position here, the roots of unity. So that's some suggestion by Alexios Polychronakos. This is what I will call freezing in the following. So you see that when you send beta to infinity, this kinetic term will be very small compared to the main potential energy, and then the beta square term is constant, and then what is left is just this Haldane-Shastry term. So that's the strategy to solve Haldane-Shastry is to solve this model and then to take the freezing limit. And how does this model is solved? You are using this this double affine Hecke algebra when you send the deformation parameter to one q to one. It's called the degenerate double affine Hecke algebra, and it's generated by two sets of generators, the coordinates, and some operators which mutually commute, but do not commute with the z's, of course. And these operators, called Dunkel operators, are have some expression in terms of coordinate permutation, which permute the coordinates of the particles. And you see that if beta is 0, the free Hamiltonian has, in this case, the Dunkel operators become kind of momentum operators. So these are kind of momenta. So you have an algebra which is generated by coordinates and momenta, and you have some particular relations for these operators. Okay, so how does one find the solution? I will not talk about the monodromy matrix for the moment. The solution of this Hamiltonian is the wave functions have the following structure. There is some prefactor, Jastrow, Gutzwiller, called in the condensed matter literature. So there is this prefactor here, and then some function of coordinates and spins. So these vectors here are just reversed spin, the Magnont states. And we can choose, one can choose the symmetry of this psi tilde to be either totally symmetric or totally anti-symmetric by permutation of both coordinates and spins. So you can choose one of these signs here. I will mainly choose the plus sign in the talk, but just bear in mind that the minus sign is also possible. So in the case where we choose the plus sign, the total wave function, since this part here, the spin part is symmetric by permutation of the spins at the position I1, IM, and the spins in the complementary ensemble. So this coefficients here, or components of the wave function, will be partially symmetric in the group of variables Z1 to Zi1 to Zim, and also symmetric in the complement. So on this space of function, we can define formally a projection where one replaces the coordinate permutation by plus the spin permutation when they are at the right of an expression. So you imagine that you act with this on this function psi. So you can just replace k by p. So this Hamiltonian here will be just the projection of the sum of squares of Dunkel operators via this projection where you replace the case. So you have the case inside you take the square of these operators, you sum them, and then you have some case left, and you replace the case by piece, and then you get you get this model here. So that's a trick which is very it's not very natural, but it's very useful. I'm confused by the buttons of the mouse. Okay, so again, this the wave functions will be given by this symmetrized components. So when we take the freezing limit, we will obtain some. So you see that when the coordinates go to the roots of unity, all the symmetric sums with powers from n equals 1 to n minus 1 will vanish. That's a property of the roots of unity. And if small n is equal to 0, then you'll get n. So in this partially symmetric functions, you see that you can replace these variables here by using this expression. You can get just a symmetric function in the Macdonald positions. So that's something conceptually we understand why we can by freezing send a n variable function into a m variable function. In principle, one can do this explicitly on this wave function, but this was never done. It looks a bit complicated. These people and also with my PhD advisors, it was proven that for example, the first component, I1 to IM are equal to 1 to M. These components of the wave function are given by, again, some prefactor, and then some Jack polynomial with Jack polynomials are some symmetric polynomials in an arbitrary number of variables with some deformation parameter. For beta is equal to 1, they are sure polynomials. Otherwise, they are just for beta is equal to 0, they are symmetric monomials. So by some miracle, in this case for Haldane-Shastry, one gets this beta equals 2 Jack polynomials. And the wave function is indexed by some partitions as you have already seen. So these lambdas here are related to the lambdas that you have seen in the beginning of in the description of the spectrum. Okay, that's it. So that was about the quick recap of the. Oops, I was promised this is not going to appear again, but it appeared. Okay, so now we can do the same thing to get a kind of XXZ long-range interacting model. The model, in fact, was suggested already in this important paper from '93, and then Uglov in '95, starting with '95, obtained a lot of important and interesting results for this model. In fact, he systematically studied this model, but since it seems so complicated, nobody dares to look at it for some years. And then Jules Lammers decided to look again at the model, and he succeeded to simplify things and draw objects to render the model more intuitive. So now everything will be q-deformed. You have this parameter q, which is different from 1, and the q numbers defined by this kind of formula. Then you have the R matrix of XXZ model, which can be written in a particular presentation in this way. Starting from this R-check. R-check is just the usual R matrix multiplied by a permutation. So the value of R check at U equals 0 is just a permutation. And then the derivative is that gives properly renormalized, gives the Q antisymmetrizer, which is symbolized by this kind of symbol. So for Q equals 1, this is essentially so the Q antisymmetrizer for Q equal 1 is just 1 minus P, the permutation, yeah, and then you have another object which is just the check R matrix, which is drawn by this braiding of two strings. So now that all this was just to explain what the permutation will become in the case of the q-deformed model. So it's now it's a non-local operator which involves all the spins from I to J through this, you see this braiding and then interaction at some site, and then you go back. So for Q, when Q goes to 1, this is just the permutation of this spin with this spin, but otherwise it's a rather complicated object. And the potential is also slightly modified. So the potential here, instead of having a double pole at Zi is equal to Zj, has a kind of splitting of the pole into simple poles. And again, the coordinates Z here are the roots of unity. So as the spectrum, there are two different Hamiltonians which are slightly different, where one is when you are considering these Sij operators with I less than j, and then you can do the same thing. So you can have this interaction here on the other side, and that will be this will be this anti-chiral version of the interaction with I greater than j, and they have this, their spectrum, they mutually commute, which is a nice property, not completely understood. But the energies, the individual energies of the two models are very much like the usual Haldane-Shastry, but with some different function, which involves some integer numbers n. So here there is a picture of the individual Macdonald dispersion law for the two version chiral anti-chiral of the model, and then if you want to add them together, you'll get something which is more symmetric, and which slightly deviates from the Haldane-Shastry dispersion relation. Now I was saying that the model has the Haldane-Shastry model has a huge symmetry, which is the Yangian symmetry. Now the symmetry is replaced again. There is a huge degeneracy.
So this is all Q real.
This is for Q real. For Q imaginary,
like root of unity, or
yeah, there are some particular phenomena that we didn't yet looked at, but for example, at Q equals I, the spectrum is very, very degenerate, and something happens there. So that's a model which certainly deserves to be looked at, because it must be a very interesting model. Yeah, And okay, of course, there is now, so the Yangian symmetry is just the quantum affine symmetry. Yeah. Okay, so now I'll try to say a few things about how one solves this model. So again, one goes to some more general model where the positions are dynamical, so these Z are dynamical, and then in order to account for this change of coordinates, we use this shift operator, which multiplies a particular coordinate by P, and leaves the other untouched. So that will be in the limit P goes to 1, will go to the derivative operator. So one gets back the Calogero-Sutherland model. In this case, the resulting model is called spin Macdonald-Ruijsenaars operator. So there is some something like the Hamiltonian, which will be again in picture will be this kind of interaction. You exchange the spins, and then you modify the coordinate of the particle by P, and there are some coefficients in the definition which are some particular functions. So when Q and P goes to 1 with this particular relation kept valid, you get back the Calogero-Sutherland Hamiltonian. So again, there is some freezing when you send beta to infinity. Beta to infinity, this means that P goes to 1. Irrespective of Q, that's when the particle frees to their equilibrium position, and then you get the Q Haldane-Shastry model. So the algebraic structure that you use here is not anymore based on permutations, but it's based on the what is called the Hecke algebra, which has the same braiding relation as the permutations, but instead of P square is equal to 1, you get this Hecke condition. So I'm sorry that there are some different conventions in different fields of integrability. So what was Q for the Q deformation now becomes T square root of T in a notation of a different field, and what was called P now is called Q. But I hope you'll not get very confused. So, okay, this in order to realize this Hecke algebra, you can either use the spin operator. So in the XXZ model, this Hecke algebra is hidden in the expression of the R matrix. You can check that this expression together with this Hecke relation ensures that Young-Baxter is satisfied. There is also another explicit realization of the Hecke algebra on polynomials of the variables z, which includes this usual permutation of z's. And these are the objects which are used to build this Macdonald-Ruijsenaars spin model. Okay, so now if we forget the spin part, we just look at the T polynomials. They are the ingredients to define some operator yi's, which are now the deformation equivalent of the Dunkel operators. So they were introduced independently in these two works. They have some expression in terms, some complicated expression in terms of Hecke and the permutations. But what's important is they obey some exchange relation with the Hecke generators. So this is called the affine algebra, and if you add the exchange relations with the coordinates, you get a double affine Hecke algebra. I'm not sure if I mentioned that these I operators mutually commute, like the Dunkel were doing. So the center of this affine Hecke algebra will be generated by these symmetric polynomials in the Y operators. And they can be considered as integrals of motion for the new model. So that's something which is known from the 90s, which is behind the theory of Macdonald polynomials. This is a field on separate field in mathematics. The Macdonald polynomials are again polynomials. They can be defined as symmetric or non-symmetric. In fact, these polynomials are the joint eigenfunctions of these operators, Y operators. And the Macdonald polynomials depend on these two parameters, which are T and Q. So that's something which was known long ago. This is a model, spinless model. Now, based on this, one can define the spin-full model. Again, by using this trick where you work with particles with eigenfunctions which are symmetric by permutation of spins and coordinates, and this is ensured by this is formally defined by the space where the intersection of this kernel of the difference between the two type of Hecke generators. And now the spin, this spin Macdonald-Ruijsenaars operator can be defined as the restriction of the sum of Y operators on this symmetric space, and this restriction will be denoted by tildes. So you see that now, if these Y's were containing only polynomial Hecke generators, this one contains also the spin generators. So now we have a spin model, and also there are higher conserved quantities which involve the symmetric sums of powers of Y's. Yes. Yes.
Instead, the algebra you had before, the algebra you had before for the usual Haldane-Shastry, in that case, you called it because it's a particular case of this.
Yes, yeah. When you send T to 1,
something like, you make something between the two constants.
Deformation parameter, which was called before Q, now is T, you send it to 1, you get back the previous structure.
And this is connected with the fact that it is degenerate, or
the degenerate is T goes to 1.
Ah, okay.
And the full is the T different from 1.
Different from 1. Okay, thank you very much.
Yeah. Okay, so I will try in the next 5 minutes to say a few words about the monodromy matrix. So now you can build a monodromy matrix for the model I just talked about by using again this XXZ matrix. Which obey the Yang-Baxter equation. So one thing you can do is to take the product as usual, the product of these R matrices, and introduce, for example, use Z's as inhomogeneities. This is not clear what this object will be, but you can do it, and you get something which resembles at what we know from nearest neighbor or inhomogeneous models. But to get the integrable structure of the long-range model, you, instead of using this inhomogeneities, you use these commuting operators, which are the Y's. So the algebra goes very much like before, but you see that now these operators contain the long-range interaction. So that's a trick to get from a L matrix looking like a nearest neighbor model. In fact, you get a long-range model. To be able to do this, you need this Daha structure, and that's not possible very often. That's the main problem. Oops. Okay, yeah. So the nice thing is that the monodromy matrix, as defined, preserves this space of symmetric wave functions that was shown by Uglov in 95. So the restriction of this, the fact that this commutes ensures that we get a normal R matrix, normal L matrix, monodromy matrix for our long-range model. And now, as we know from the Yangian case, the Q determinant of this matrix commutes with all the elements of the matrix A, B, C, D, and as such, and it generates. In fact, this Q determinant generates the integrals of motion. Here, I put. I consider the case of the inhomogeneous usual and inhomogeneous model, but if you instead of Z you put I or Y, so you will get you'll get an object composed from symmetric polynomials in Y's. So these symmetric sums and their restrictions will be commuting with L, and that's the origin of, in fact, of the quantum affine symmetry that I was mentioning before. And that's why we have this huge symmetry of the model. And this is transported in some sense from the Yangian to the deformed case. So now if you want to go to, so that was the structure of the dynamical model. Now if you want to go to the Haldane-Shastry model, purely spin model, you have to send this parameter Q to 1. And then expand the Hamiltonians in powers of Q minus 1. The first is trivial, and then the second is this Hamiltonian that was simplified by Jules in a few years ago. And that goes also for the, you can do it for the generating function of conserved quantity, this delta. You can, this object here contains all the conserved quantities of Q Haldane-Shastry. And as a bonus, you get the dispersion relation freely, because you know what the energies are for the Macdonald operator. Davide, you have a question or no? Okay. Okay, so that most of these are things that were known before. So our contribution was to get the wave functions, to get explicit expression of wave functions again. So the wave functions are indexed by these motifs. And the simplest thing is to get the component, the first component of the wave function where I1 to IM are 1 to M, and then evaluate them at their equilibrium position. So the expression that we got is contains the Macdonald polynomial for some particular parameters of Q and T, which is the equivalent of this Jack polynomials at beta equals 2. And then we get this symmetrized Q van der Monde factor, which we didn't, well, this part we were expecting, but this part it was not clear how to get. So the proof is very complicated. I will not bother you with this. just to mention that the other components, arbitrary components of the wave function, where i's are transported somewhere else, are just given by symmetry. They are given by this action of polynomial Hecke generators, which act on this, the first component. And this complicated symbol is just to say that, well, it's the action of the Hecke generators. Okay, so this generalized the construction of the ordinary highest weight vectors. The descendants is a more complicated story, which is also not completely understood for Haldane-Shastry. So there are a few things from the mathematical point of view that one would like to understand how to do this construction for, directly from the freezing procedure. There are some relation for the non-symmetric Macdonald polynomials that must be hidden beyond. The other point is how to build the other highest weight, the other vector than the highest weight vectors. So there is some Gelfand-Zeitrin construction that was sorted out by Uglov for the usual Haldane-Shastry model. I think this is these questions are related to the question of the separation of variables. Then there is also the fermionic formulation of the model, which where one can use the vertex operators, and this is very important to look at the CFT limit, and so that this is also something that is interesting to sort out. Then there is this limit. Since we have an extra parameter, we can send this parameter to infinity, and then the model becomes particularly simple. There was a paper recently by Pasquier and collaborator about this limit for XXZ. They got an interesting exclusion model, and I think something similar but more symmetric can come out from this from the model we are looking at. And then an interesting question is how to define a q-Inozemtsev model. Particularly the hyperbolic in the hyperbolic limit, we have seen with Matthias, we have used this analytical continuation of the roots of unity to some real parameters. It's a good question. What will be this model? Again, there will be an extra parameter kappa, which will be useful to tune in order to study what happens, for example, with the bound states that we expect in the in XXZ. What happens? What kind of bound states we have? What happens with them in the limit when the interaction goes to nearest neighbor? And then there are some aspects which are interesting in the framework of generalized hydrodynamics and transport. There were some very interesting results by several groups, including the group of Denardis, for concerning XXZ model, some KPZ scaling in the transport. They made a conjecture that this scaling is related to the existence of some non-abelian symmetry, like the SU2 symmetry. And the question is what happens for other models which have SU2 symmetry. Also, it seems that the bound states play a very important role in the transport in that case. The question is what happens since here we don't have bound states anymore, what happens to the to the transport in this particular case. So I think there are many interesting questions that one can still study about these models. And thank you very much for your attention.
Okay, so
very quickly, if I'm not completely wrong, there should be a connection between these models and actually the algebra and so on, and partition function of n equal to super Yamits in 5 dimensions. Some sort of are these the algebra the same? The spectrum is the same for that say instant-on partition function.
This kind of model, the spinless model, of course, is
yeah, probably only spinless. Yeah, there is only spinless. Yeah. I don't know if someone has constructed also with the spins on the gauge theory
that's
side.
a good question. I don't remember to have seen anything about the spin model in this context, but yeah, of course. Yeah, there is a lot of structure which was studied in the case of
because you have a Virasoro, no? Deformed Virasoro in 4-dimension Virasoro, and in 5-dimension deformed Virasoro, which is behind your structure, isn't it?
Exactly. Yeah. So we are discussing with Jean-Emile about this to try to bridge the two. Yeah. Yeah.
okay, we have an online question of Gleb Arutyunov. He has no question anymore, it seems. Okay, I saw, yes. Okay, so maybe Matthias, then online question.
I don't know what I'm supposed
can
to do.
Can I ask question, Didina? This is Gleb.
Yes.
Can I ask you? There is so you're talking about spin Rausner-Schneider model, yes. And there is one which was introduced by Krzywer and Zabrodin, but I guess this is not that model which you are discussing, right? Your model is, I mean, spin interactions are different from that.
Yeah, spin interaction is via this Hecke operators.
So my question is it related to this model introduced by Krzywer and Zabrodin, or this is different?
No, I don't think so. Mm-hmm. I have to check.
Okay. Thank you.
Thanks.
Okay. Yes, Matthias, you had a question too? Matthias, I don't know if you are speaking.
Okay, yeah, I was not permitted to remove this. I mean, yeah. Anyway, now you can hear me. Hi, Didina. Thanks for the nice talk. So, since you went back to these long-range models, I was just wondering, do you see anything here which we might, in the end, be able to recycle again into ADS-CFT and really make this long-range spin chain picture live for ADS-CFT? I mean, in particular, this is nice. I guess that was known for a long time, but still, I mean, this nice formulation of using the R matrix and monodromy, but sticking in operators into the monodromy. I mean, it's really a kind of conceptual question, but do you still think in the end one might be able to describe ADS-CFT not only by some quantum sigma model, but equivalently by some real nice long-range spin chain?
Yeah, in fact, yeah, that's a long-standing dream to be able to find an algebraic structure for the ADS-CFT integrable model. I still have a hope, but it's not really obvious how to do it. So one problem of these models we are looking at is that they have dispersion relation which is quadratic, and there is no real, we don't see any trace of the crossing symmetry, if you want to. We don't have antiparticles in the model, so that's something that the ADS-CFT model really has an important ingredient. The ADS-CFT model is a field theory, and as such, it has antiparticles. So hopefully, at some point, we'll find a long-range model which has antiparticles, but we're not yet there.
I guess another thing would be to really find this structure of, I mean, basically some kind of quantum spectral curve for these models, right? And then,
yeah, so we're trying to make small steps, like understand what the Q functions, what's the relation between the Q polynomials, Q functions are, and the structure of the wave functions in the long-range model. So these are, of course, important questions to solve before going to add something to the model in order to render it more closer to what we want.
Thanks.
So actually, this is a bit related to Matthias's question, because so one case, and we discussed this a while ago, then we sort of ran out of steam. One case in ADS-CFT which has some features that are similar to what you were telling us is this pure SNS ADS-3, which is also a Vesumino-Witte model on the worksheet, because there are no bound states there. The dispersion is not quadratic, but is linear, so it's even a little bit different. And there are some qualitative features that might look a little bit like this, but at least at the time we were not able to sort of pinpoint it. I was wondering, perhaps, because you mentioned that when Q is a root of unity, in some case you can get huge degeneracies. Another thing that these models have is that they have much larger degeneracies that you would normally expect. Whether some of these features maybe you have started to encounter, perhaps, like going from quadratic to linear dispersion or things like that. Anything rings a bell in this sense? Or?
Yeah, so I think one of the important things to do will be to look at what happens when Q is a root of unity. There are still, I mean, there are still secrets for XXZ, nearest neighbor XXZ, that we are discovering. I'm sure that this model has a interesting structure at roots of unity. Yeah, so then coming back to the relation to Vesumino-Witte models, we already for Haldane-Shastry there is a very nice link with Kac-Moody, because in this CFT limit the model becomes in fact Kac-Moody, two copies of Kac-Moody in some sense. So of course this structure gets deformed in the q-deformed case. It's not, I don't expect that this Q deformation will be obviously related with what we know, at least not at in ADS-CFT, especially not at Q real, but who knows what happens at Q root of unity. So yeah, well, all these are interesting questions, but not much progress was made on the subject, and it would be nice to have some more work devoted to this. The nice thing is that Jules will come to Saclay next year, so he's not anymore at the other end of the world. So hopefully we'll
maybe a quick follow-up. Those plots that you showed for the chiral and anti-chiral dispersion, can we just trust them at Q root of unity, or the way that they are derived only makes sense for Q real?
No, the expression should be, the expression of the dispersion relation doesn't change. What might change is that some states will happen, will disappear, or something will happen to them at some point.